Hi, I'm Antonio Sala, and in this video we will continue with this case study of controller structure design for this two-tank mixing and heating system. Our primary control goals are outlet temperature and dilution, concentration of the reagent diluted in water, and we also wish to control tank 1's level for safety. And in a first video in this case study, we discussed a basic multi-loop structure in which we dismissed one manipulated variable, the steam inflow, and we also dismissed 4 sensors, 3 flow ones and 1 temperature sensor. This was, let's say, the simplest option. We can save in the extra instrumentation needed, but if this didn't have the correct performance, then we would need to increase the complexity of the controller structure to meet more stringent goals in temperature or concentration. So we will indeed use all available instrumentation in this second video. So we will start with our proposal for a more sophisticated level control structure. Let's go. The basic multi-loop one was just using level with the second manipulated variable, the valve in the water inlet pipe. But if we have a flow sensor, then the obvious choice is using cascade control. So my level sensor transmits its reading to a level controller, which acquires set point from the operator console, and then the output of the controller will be a set point for FT2. So slave flow controller receives such a set point, and it's that slave controller, the one which operates the water valve. So this will be our first proposal for level control. But there are 2 pending issues. First, that increasing this FT2 will change the ratio between reagent and water, so it will have some coupling with the concentration control, but nevertheless we'll discuss that later on when we discuss the concentration loop. And second, the level variations will be mostly originated by changes in the downstream flow demand, which is a disturbance, an arbitrary one, but as it is measurable, then we may wish to add some feedforward components to this level control. For instance, for each liter out, we need 1 liter in, but okay, as the nominal ratio is 1 reagent, 5 water, then the proportion of water is 5/6. So we'll multiply this flow reading, well, actually, let's say the increment of flow with respect to the nominal value, as usual when we do linear control, then we'll multiply that increment by 5/6 to get the required increment of water flow, so that increment will be added to the set point for the slave flow controller. Of course, the fraction of the reagent will be 1/6 once diluted, so we still need an extra flow, but that 1/6 will be achieved by a ratio control structure we'll discuss when dealing with the concentration control. So for the moment being, this will be our level control structure, and the remaining bits regarding the coupling with the concentration loop we'll discuss in a minute. If I just draw the control components and not the process elements, this is the block diagram that summarizes what we have designed. Level transducer and level set point to a master PID, and then a cascade slave controller gets a sensor reading from water flow and compares it with the sum of whatever the level controller sends and the feedforward component from the outlet flow sensor, operating over the water inlet valve to achieve the desired set point. So this is it. let us now discuss concentration control, but in order to avoid cluttering in the diagram, I will delete all these lines and blocks corresponding to level control so that we understand concentration control starting from scratch. So let's do it. If we recall that the nominal operating point is this one reagent 5 water in units of flow or stored volume, then a first option for concentration control could be the open loop one. I mean, if we are sure about the purity and the precision of the flow controllers, we may propose a slave for flow controller using this sensor operating in the reagent inlet valve, and then if I multiply whatever water flow gets into with the nominal ratio 1 to 5 to get FT1 set point, then in theory this would work, because for every 5 liters of water coming in, 1 liter of reagent will also come in. So this could be good enough in practice. However, if the purity of this reagent changes, so nominally it may be 100% pure, but actually it may range from 92% to 99%, and it's unknown, such a purity, okay, that would disturb the concentration. And also, if the flow meters are not well calibrated, then maybe I do not get the required ratio between the flows, so the overall resulting concentration isn't wrong. So if I have a concentration controller, of course assuming it has greater precision than that of the flow meters, otherwise this would be nonsense, but okay, if I have a precise concentration controller and I install it in tank 2, then I can change this constant ratio by a varying ratio with a ratio control scheme as follows. Instead of multiplying by a fixed 1 to 5 ratio, this concentration sensor will be read by a concentration controller fed also with a primary concentration set point, and then if there is a mismatch between the set point and the sensor readings, then I would propose an increment of ratio that would add to the nominal ratio, which in this case we assume is 1 over 5, and then the actual ratio is the thing that would be multiplied by the reading of FT2 to get me the actual FT1 set point. So we will keep this as a final proposal for concentration control. And in this way, we will solve the coupling from the level controller to the concentration controller, because when the level controller operates this valve and changes FT2, then FT1 will track those changes multiplied by the suitable ratio in order to keep concentration constant. We may have a question on, well, what about feedforward of this disturbance? But well, we can realize that this feedforward does not have a direct effect on concentration. The only effect of changes in outflow are into levels. So as this does not change the concentration, we will not implement any feedforward stuff in the concentration subsystem, because the effects on the level that would translate to increments in FT2 are suitably decoupled by this ratio structure, so that indeed they do not influence the concentration loop. So there is no need of feedforward here. If we summarize what we draw, we have the error between the set point and the sensor reading fed to a concentration controller whose output plus the nominal 1 to 5, in this case ratio, gives me the actual ratio that multiplied by the flow gives me the set point to the slave cascade loop acting over the reagent inlet valve. So this is a summary of these drawings here. Good. So the only remaining thing is discussing temperature control. And again, we'll start from scratch to avoid clutter in our drawings. Let's go. We have two manipulated variables, a heater in tank 2 and a steam supply valve in the inlet heat exchanger, which could be used for temperature control. In a basic multilevel structure, we have to choose either VM1 or VM3. In here, we'll use both in a cascade way as follows. We'll first consider that our main fast control loop is built by feeding this sensor to a temperature controller which acts over the power level of this heater. Then we will assume that we wish to keep this heater in, say, 50% power level so that we have enough room for unexpected issues to be handled by this heater by increasing or decreasing its power. So we will compare this with a 50% VM1 set point. And if there is a difference between the set point desired value and the actual value, a PID controller or whatever controller we need will be in charge of operating the steam valve. So this is a cascade structure with extra manipulated variable in which we have the master fast loop and the slave slow loop. How does it work? Well, imagine that for whatever reason we detect that water in tank 2 is too cold, so we increase VM1 to 90% of its power range. What does it mean regarding the steam valve? Well, if we need to increase the heating power of this heater here to almost saturation, it means that we should add more steam in here so that the remaining heating power needed in here reduces. So when this error signal is negative, because 50 minus 90 gives negative, then this thing should also have a negative gain in order to open this valve. So, okay, I think it's better to change signs here so that when this thing is positive, we need extra power from the steam valve. So a positive gain PID would solve the job. That, of course, its effect is slower because, okay, we have to heat a lot of metal masses here. We have to heat up all water in tank 1 before it reaches, let's say, tank 2. Okay, then we have a fast VM1 loop that slowly, in the long run, if it has a deviation from 50%, will be corrected by VM3. So this would be a sensible enough temperature control loop. However, we forgot that we have a temperature sensor here. So how can we use this? Well, we need to alter this first temperature control structure as follows. What we need is to incorporate an intermediate cascade with extra sensor as follows. This slave loop would provide, instead of a manipulated variable value, it would provide a set point for TT1. So if this is operating almost to full capacity, it means that the temperature in tank 1 is too low. So this controller should tell that we should increment temperature 1. So we will compare it to this output of the slave slow controller in the previous structure, so that we have a second slave of the slave, temperature controller that operates VM3 in order to achieve a desired temperature in tank 1. So this will be almost, because okay, we forgot feedforward, but okay, keep this in mind because the basic feedback strategy for temperature control will be this one. So now we need to discuss again what happens with FD3. If we have, extra output flow required. What do we do with this thing in the feedforward in the temperature control? Shall we do anything? Well, yes and no. In principle, we could think that if a flow increase is detected, we could add some feedforward stuff, immediately increasing the heating power of this manipulated variable. But it's not as easy as it sounds, because okay, if tank 2 is filled to a given temperature, then we do not need an instant increase of heating power. We just need an increase of heating power as colder water comes from tank 1. So this feedforward, ideally, this should not be static gain. It should have some slow dynamics, let's say, some first order stuff here. So we would need extra care in designing it. So even if it could be an option, maybe, okay, if we think that the effect of this flow exchange of over temperature is slow, then maybe we could think in assigning that feedforward to one of the slave loops, either in here, increasing the TT1 set point, or on the steam valve. But, increasing TT1 set point, okay, that does not seem to make sense, Basically, when there is more flow, I just want more water, but to the same temperature. So it also does not seem sensible to do some feedforward of this thing in the temperature stuff. So maybe the solution could be multiplying here by perhaps a gain, because the steam valve has already slow behavior, and then adding this to the steam valve command. And indeed, this could work. And we could keep this as a final proposal. But there is still slight improvement we could think of, in the sense that realizing that basically outflow stuff does not directly influence outlet temperature, then what does really influence outlet temperature? Well, outlet temperature basically will be influenced when these flows increment for whatever reason. So if these flows increase, it's then when I should do something with the steam valve to keep temperature. So indeed, these flows could increase because of an increase of FT3. That's what we just drew. But they can also increase because somebody changes and, let's say, increases the level set point. If the level set point is increased, even if this demand does not change, then this flow would increase and the liquid would come cooler because I would need more heating power. So instead of doing a feedforward here because of FT3, in order to be protected also to level set point changes, what we should do, and that will be the last proposal, is reading the total flow entering my system and comparing it to the nominal total inflow, assuming that the specific heat of this mixture is close to the water specific heat, okay, because otherwise, if specific heats are very different, then we should somehow do some ratio stuff, but okay, forgetting about that, the actual need of steam heating power here to avoid disturbing downstream whatever happens depends not on outflow, but in total inflow. So it's this thing which, multiplied by some feedforward term, will be the thing that should be added to this PID output in order to operate on VM3. But the name of this is not correct, because FT1 and FT2 are, the set points of these things are decided by the level and concentration controllers or whatever, so these are sort of controlled variables, or, well, the set point is a manipulated variable. So when the output of one control loop influences another control loop, this is not called feedforward. It is called decoupling. So whatever the name we give, the theoretically good name would be closer to decoupling, the effect of the level and concentration loops. So this is decoupling, this is not feedforward. And this final structure is the one that we will summarize in this block diagram. So if we revise, we have a master loop in which I get the primary temperature set point, and the PID acts on the heater, and if there is a difference between 50%, then we react on a slow loop, and the first slave decides which is the value that we should achieve in the temperature of tank 1, and we read that sensor, and if it's not correct, then we act over the steam supply, and if the total inflow is different from the nominal one, then we increase the steam supply opening. So this summarizes the drawing in here. So to conclude, we have shown how to complement this basic multi-loop structure by adding extra manipulated variables and sensors, and we finished proposing these temperature, level, and concentration proposals for our final control structure. We end here. Thanks for your attention.